5.1. We're going to go back in our notes from where we left off on Thursday and pick up a few more examples just for review of what we're doing here. Recall that we are looking at what we call an indefinite integral, and that this part of it is a derivative. And our task is to find out what is the function that would yield this derivative. We have a basic rule that we're going to use. So we're going to, I'm going to first of all write this as x to the 3/4 power plus 1 and dx. Now whenever you write an integration, an indefinite integral like this part of it, called the differential x, is telling us what the input variable is for both our derivative and for the resulting function. Our basic rule is this, and I want you to write out the work as you see me do here. The first step is to add 1 to the exponent and then divide by that new exponent. Moving on to the next term. If we have just 1, that's the same as 1 times x to the 0, so we'll do the very same rule. We're going to add 1 to the exponent and divide by the new exponent. Now there's going to be infinitely many functions that have the same derivative. They differ only by some constant term over here. So we're going to put a C for constant term. This now is the function f of x that when we take the derivative of this function, we should go right back to this, what we call the integrand. So let's see what f of x equals here. This would be x to the 3/4 plus 4/4, so that would be 7/4 power, divided by 7/4, plus x to the 1 divided by 1, or simply x, plus c. We're going to take care of the dividing by a derivative by writing that, dividing by a fraction, by remembering that when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So we have 4/7 x to the 7/4 power plus x plus c. Now again, to check this, all we have to do is take the derivative of this function. So we would start with multiplying the exponent times the coefficient and then subtracting 1 from the exponent. The derivative of x, as we know, is 1, and the derivative of a constant, any constant, and again this stands for any constant number, is 0. So our derivative would be, the 4's cancel, the 7's cancel, x to the 7/4 minus 4/4, or x to the 3/4 plus 1. Let's compare that to what we started up here. And again, if we write the radical as a fraction, we have the very same value there. To do this with the Inspire, so let's take your Inspire, get into a calculation page, go to Menu, go to Calculus, go to Integral. We're going to ignore the lower and upper bounds, which is Tab and Tab. In here, let's go back, we had the 4th root of x cubed. So if we do Control on the exponent key, we can put in the 4th root of x cubed. And we need to remember that it's plus 1. So if we go back here and move outside of the radical, we don't want to put the plus 1 under the radical. We have the integrand that we started with over here. And if you tab, then remember we have to tell it what the variable of integration is, the input variable here. So we'll type x and press enter. Now our answer isn't the same thing as what we have on our work. Let's take a look at it. We said ours was 4/7 x to the 7/4 power. Would that be 4/7 x to the 7/4 power? Now, I don't know why it doesn't combine these for us, but if we have x cubed to the 1/4, we're going to have x to the 3/4. If you multiply terms of the same base, you'd have x to the 3/4 times x to the 4/4. We add the exponents. Would that give us x to the 7/4 power? And the answer is yes. If in doubt, remember we can check. We'll go up here. Let's bring that down. Say equals, and then we'll put in our answer, 4/7 x to the 7/4. So we'll have the fraction, and we want 4/7 x raised to the 7/4 power, and we have to finish it by saying plus x. Make sure you bring the cursor down like that, plus x. Now, because c stands for any constant, you can either make it plus 0 and leave it like this, or we could put any value there. But let's leave, because we're not taking the derivative. So let me back off on that. Let's just put a plus 0. Let's leave the constant off. Press enter. And our values are not looking the same. However, we know that if we take x to the 3rd to the 1/4. Now, the reason why the Inspire's being kind of picky about this is that if we are taking something, the 4th root of something, we need to be careful about whether it's a positive or a negative root that comes out. And that's what's implied here. Okay, let's go on. Let's look at our next problem. Again, determine the integral of this. This is our derivative, and we have a value u there. So on first look, it looks like we've got an integrand that we've never seen before. How are we going to use our basic rule? Well, if we multiply the square root of u through each of these, we're going to end up with u to the 1/2 times 1, so that would be u to the 3/2. Plus u to the 1/2, and then we have our differential u. So now we can do the same thing that we've been doing. We're going to add 1 to our exponent, divide by our new exponent. That would take care of the first one. And our second term, we'll do the same thing. We will add 1 to the exponent and divide by the new exponent, and then we have plus c. Remember, we are finding a function that when we take its derivative, we'll go right back to the derivative that is our integrand in our problem. So we have f of u equals, and this is going to be u to the 3/2 plus 2/2, or u to the 5/2, divided by 5/2, plus u to the 1/2 plus 1, that's 1/2 plus 2/2, so that would be u to the 3/2 divided by 3/2 plus c. And again, we can simplify dividing by a fraction. I would expect that you would do this, so be sure you do this one last step. To divide by 5/2 is to multiply by 2/5. And to divide by 3/2 is to multiply by 2/3. And so this would be our answer. Again, to check this, we would need to take the derivative. And if we take the derivative of this function, we would have 2/5 times our exponent, our coefficient times our exponent, and we would subtract 1, plus the next term would be 2/3 times the exponent, and divide, or raise it rather, to 3/2 minus 1. And of course, the derivative of a constant is going to be 0. So the derivative would be, and the fractions are going to cancel, u to the 3/2 plus, again, our fraction is going to cancel, u to the 1/2, and is that the integrand that we started with? Well, it is if we look at it in this case. And again, we could factor out a square root of u and get back to that. So our answer is again the function. So this will be our answer that we would have to that. Moving on to our next problem here. If we were in class together, what I would do is assign certain groups of you to have different values of c. So we'll just kind of do this together here. Let's say that c is equal to, well, we'll start with c is equal to 0. I'm going to go over here. We're going to pick up a graph page here. And I'm going to put in x cubed. And that is our function. I'm going to change the window. I'm going to make this -5 to 5 and see how that looks, if we can get a little better picture on this. So we'll make it -5 to 5, and I'm going to scale it by 1. And I'll just make this an easy one, -5 to 5, scale by 1 also. And we'll take a look at that. It's a little different view of it. Okay, a little easier to see. So that would be the function, and let's just move this in this direction. The function that has c as an constant term. Let's try it with c equaling 2. So now what I'm going to do, I'm going to tab, and I'm going to put in the very same thing, x cubed, and now we're going to say plus 2. What we end up with is actually the same function. If you recognize this, it's going to be just a vertical translation of this, and then we should cross it at 2 here. And sure enough, it crosses at 2. And we'll just do one more. Let's say c equals -3. And we'll tab, we'll get a new one here, x cubed. And we'll say then subtract 3. Now if that's the case, we take the x cubed term and it should cross somewhere down here. So let's see if in fact it does, and there it is. So we have 3 functions. They're all the same. They look a little different only because we are looking at them from different output intercepts. Now what I'm going to do is, and again we would do this in class together, but we can make a point here. Let's put a point on, and I'm going to put a point on each of these. It doesn't make any difference where it is. So we're going to change those coordinates in just a minute. What I'd like to do is I'm going to change the coordinate, and we're going to change this to be a 1. So on this curve, I'm going to make the input value to be at 1, and we end up with a point at -1 and 2. We're going to do the same thing on the original curve. And not surprising, the coordinate of the input is 1, the output is 1. This is for our x cubed. And we'll move this coordinate over here, but we're going to change that also to be a 1. And its output now is 1, 3. So we have these points now lined up. They're all vertical. If we look then at a tangent, we'll put a tangent at each of those. Maybe some of you know where I'm heading on this. I'll put a tangent at each of those, and let's do a measurement of the slope. Now, what should the slope be of each of these tangents? Think about what is a derivative. The derivative is the slope of a line tangent to a curve at a point. And so I have 3 functions. They're all very similar. They differ only in the constant term. If I think about the derivative of each of these 3 functions, what is our derivative? Same thing, right? So if I look at the slope of each of these, I'll just move them to the side of that. the slopes of each of these tangent lines is the same thing. Is that consistent with